Thank you, Grace, and thank you, Arnold. That was a very good segue into my talk, where I am talking about emerging capabilities and moving from inspection to intervention, specifically this time with a small ROV, specifically the Seabotix ROV, and a manipulator arm. So currently, it's mostly for inspection that they have these small ROVs, and we're trying to increase the capability through Autonomy software and through the partners at Teledyne to increase the capability of the EOD warfighter. So quick summary about SeeByte. We do software. We only do software, and we're based in Edinburgh, Scotland. We have a pipeline of PhDs coming from Heriot-Watt, and we specifically focus on the maritime environment. So we deal with oil and gas and navies throughout the world, and also oceanography, and we specifically target autonomy, sensor processing, and things like that. And we also have a small office in San Diego that I am in charge of with about 5 people here where we're supporting mostly the Navy, pretty much solely the Navy at this point for the San Diego office. So this talk is going to be a general overview of where we are today in ROV technology and ROV autonomy, and also how we got here through the eyes of SeeByte. So we started with autonomy and ROVs in the oil and gas industry. We didn't start it in the navies. And we started with work class ROVs. Work class ROVs are about 10 feet tall, 8 feet wide, and they do all the construction underwater. And they required very highly skilled pilots to be able to not only fly the ROV, but also work the hands. What they're seeing was it would take really long time to be able to do very simple tasks underwater because of how much current was pushing even these very large ROVs, and they needed to get that time down to be less. So because every minute, every hour you're at sea is just money that's churning away, and every minute that a oil rig is down, that's also money being spent. So I want to show a quick video of something that we did in 2006. So this is a work-class ROV with manipulator arms trying to put a shackle through a hole. It's a very simple operation. Normally, if you were to do it with your own 2 hands, but underwater with currents, and also dealing with the kinematics of the 2 arms, the kinematics of the ROV itself, you can see that it becomes a very difficult problem. And so this shows just a clip of what these operators were doing when they were trying to get the shackle in, and they were actually never, not to give away the ending of the video, but they were actually never able to get the shackle in there manually. They tried for about an hour and a half for this particular one, and we clipped out the section where they got the closest. But as you can see, right when they try to move the arms, the ROV will move itself. So you have 2 pilots, sometimes even fighting each other, trying to do these missions. See, I almost got it, but not quite. And pretty soon it's going to switch over to where you actually have CoPilot installed on which is our dynamic positioning software on the ROV, and that's the complete task from start to finish with CoPilot on there. And not to give away the ending, but they'll actually get it with the CoPilot. So close. And again, this was so now you have C-track, and now you can see that there's actually no pilot anymore. At this point, the pilot is out of the equation, and the only person that's actually manipulating anything is the one with the arms. So with autonomy, you can assist these pilots to do a lot more underwater and to be able to actually finish these tasks much quicker and to do tasks that they were never able to do before. And that's mostly what my talk is going to be about, is what can we now do with small ROVs now that the technology is shrinking down and the capabilities are increasing both electrically and mechanically. What can we do with controls to be able to do even more things underwater? So in 2006, we took what was almost an impossible task, and we reduced it to a fairly easy task that was done in a couple minutes. There we go. So what has SeeByte been doing since then? We've kept hard at the ROV industry. Ooh, that's not the right button. So with SeeByte, we do a lot of projects. We do a lot of R&D projects with the Navy, and also with hardware manufacturers. So if you look at, we started in 2006 with a product that was brought to the oil and gas industry, and since then we've been doing projects. We've been having an O&R project with a hull neutralization, or a hull inspection and neutralization ROV. It looks like an AUV, but this one is actually an ROV with a tether, but it has the cylindrical shape. It doesn't show up too well, but it's doing an orbit around an object of interest. As maybe a lot of you are already aware, we were doing the SSR Wind project, doing the autonomy on that one. That one had an arm, and it had a Teledyne Benthos ROV, and that shrunk down the size of the work class ROV to maybe the size of like the table, or a little bit smaller than that. So still a pretty large arm, pretty large ROV, but it was proving that we can start doing things with smaller vehicles. And most recently, in the last 2 years, we've been in the UK. We've been on the MOD disposal unit ROV, where it has visual target tracking, autonomous neutralization, autonomous manipulation of objects. And in the US, we've been working with the Unmanned Vehicle Lab, which was also a part of the SSR Wind. They've continued that on by purchasing a Seabotix vehicle, purchasing an HDT arm, and also providing a space for the integration of that to happen. And I'm going to be showing a lot of videos and pictures from that integration over the last year, and also some of the technical details and possibilities for the future work of this type of stuff. So why do you need arms on small vehicles underwater? And it's basically, the obvious reason is to get the diver out of the water. Divers it's an inherently dangerous job to be able to go underwater and do manipulation, and also you're limited by the amount of tanks and boat space that you have for all the equipment for divers, and the amount of air that the divers need to be able to work. So by putting an ROV underwater, you can completely take the diver out of the water and do manipulation of things that you may not have even been able to do before. And that's not just for mine countermeasure, for the more obvious reasons. There's also doing things for aquaculture, for nets, and for hull cleaning, for just normal ships, and basically anything that there's a dangerous job out there that's happening underwater. It could be done with a small ROV. In addition to that, the large work class ROVs, sometimes you don't need a large work class ROV to do all the things that need to be done underwater. Sometimes you just want to be able to go out there with a small ship, throw in an ROV, and have it do something light, so light work. So the Intervention ROV project was done through favour and the Unmanned Vehicle Lab. It included Teledyne Seabotix. Also, Teledyne RDI was a part of it through Seabotix, where they were able to get a DVL to a much smaller package to be able to, and also be able to get the vehicle lower to the seafloor, so that you can do more work lower to the floor. And the manipulator arm was done by HDT Global, and SeeByte was providing the software. So I'll be talking mostly about the software, but also just kind of about the project in general. There were 2 phases of the project. The first phase for SeeByte, there was definitely other work being done, but the first phase for SeeByte was to take an EOD vehicle with just different sensors and to put dynamic positioning on it, to make it hold station, to make it move at a continued rate with a hands-off operation from the operator. And then the second phase was to do the same thing with the vehicle that has an arm, and also added 2 more degrees of freedom for stability. But this is all COTS equipment, and for the integration effort. So there was no specific requirements from the military to us to perform actual tasks. It was just, let's see what we can do with an arm and a vehicle and some software. So the first configuration was a Seabotix vehicle. It had a Blueview 900. The Teledyne RDI Explorer, so the larger package, it had just a regular Seabotix manipulator, the Tritech, USBL, and also SeeByte CoPilot. Configuration 2, it had the HDT arm, as you can see. It was a 4-degree of freedom arm with just a simple pincher at the end. And we also added, or Seabotix put on outboard thrusters so that you could add pitch and roll control, or pitch and roll stability in this case, so that when you're moving the arm or when you're picking something up, then the vehicle can counteract that and it not move, the tail wagging the dog. So once you do something, the vehicle can stay steady, because inherently the vLBV doesn't have pitch control. So I'm going to be showing you a series of pictures and videos, and also kind of going through the process to get the control onto the vehicle. And I just wanted to start out with just showing you the vehicle itself. This one has the Pathfinder DVL, so the DVL is a little bit up in there. Point to it. So the Pathfinder DVL is up above the forward-looking sonar, up in this area. This one actually had a Tritech forward-looking sonar on it in front. And this is the 4-degree of freedom arm, so each joint has 2 degrees of freedom, and then the pincher at the end. And also Bautech had a camera on the end of the effector and also inside the vehicle. So the things that we needed to do to get CoPilot, which was just a piece of software on a work class ROV, to the main user interface for the Seabotix vehicle, was we had to pull in a lot of other things. In the upper left-hand corner, you can see that CoPilot is actually running on the upper right-hand screen, but they still have 5 other screens showing video, sonar, vehicle diagnostics, things like that. So we had to pull all those other things into CoPilot and have them be pop-up windows, because you typically don't need all of those things at the same time. So that was one thing that we had to do. Also, and this is the main underlying reason for this, is that you can see the operations of work-class ROV is from a big ship where you have a room for all these screens, and on the bottom you have a very small rib. So there's no room for more screens, more laptops, more things like that. So we made it a big effort to make sure everything is available through one user interface. And that was the easy part. The hard part was the control. So here is the fundamental equations of ROV stability. I'm an engineer, so I have to put a couple of equations. What happens is the work-class ROVs have a huge stability moment arm, which is the top equation, and that's defined by the distance between your center of buoyancy and your center of gravity. Also the mass, the weight with the W term, of the vehicle itself. So when you go from these huge work-class ROVs down to these small ROVs, your stability arm and the amount that the vehicle will stay stable gets reduced a lot. Also, when you start putting things under the vehicle, like an arm, then you have an asymmetric drag profile. So we're going to have more drag on the arm, you're going to have more drag under the vehicle than you will on top of the vehicle. And that's going to be a function of the square of the speed in the force drag equation. So in the bottom equation, you have two forces fighting against each other. The stability arm, which is linear and stable and just it's just one equation. It doesn't change over time or speed. And then you have the force, the difference of force, which is going to just change as the square of the speed. So the faster you go, the more unstable you're going to be. So it becomes a pretty difficult thing to do when you're doing it with the smaller ROVs. I want to quickly go over what does it mean to add autonomy, and what does it mean when we're adding these capabilities. And so basically there's a hierarchy or steps that you do with autonomy. At the very bottom level, you have manual controls and all your thrusters, and your user has to input everything. They have to input the goals, the tasks, and also the position of the vehicle to do something. As you move up in your hierarchy of autonomy, you start helping the operator, so you have operator assist, kind of like a cruise controller for your car or dynamic positioning. And then you move on into tasks. Go inspect a wall, go inspect a ship, and then you let the vehicle go on its own. And then eventually, years from now, the goal is to have full mission goals input into ROVs and that can do the same thing as a human normally would. So right now, for ROVs, we're moving into the operator assist with dynamic positioning into making it do tasks. For AUVs, we're actually pretty much at the top of individual tasks and moving on to full autonomy, where you can program a fleet of AUVs, put them in the water, and they go do a goal mission and come back when they're done. But we're still pretty low on the ROVs, and that's what we're getting to. So real quick on the CoPilot interface, so you know what you're looking at when I start showing you all the 10 minutes. Okay. So looking at the CoPilot interface, the ROV is in the center. There's a forward-looking sonar that's in front of it, and on the sides and top there's diagnostics. But just to make sure that everybody knows what they're looking at as I go through them. This is a picture of, we had both ROVs in the water, and one was actually target tracking the other while we were looking at an object of interest, is what I'm calling everything. So the vehicle with the arm is target tracking the object of interest, and we were target tracking the other ROV. So as we would orbit, both ROVs would actually orbit around the object of interest. It was kind of we didn't mean to do it, but it was a pretty interesting byproduct of having everything in the water and target tracking each other. So this task was an inspection. We're also doing a lot of floor manipulation. So what this picture is showing is one ROV looking at the other with the arm. You can actually see the arm in the shadow of the sonar, and the ROV is almost on the ground in dynamic positioning, manipulating an object of interest on the seafloor. Another task would be to inspect a pier, find an object of interest, and touch it. So that's what this is showing, where the ROV is touching the object of interest. We're in complete dynamic positioning, and there's a pier behind it. So here's a video. Here's a video of, from the ROV's point of view, trying to touch a target on a floating object of interest. And in this case, the object of interest is also spinning. You can't really tell from the video itself, but this one required not just the person manipulating, but also still required the pilot to be able to move itself in relation to the target as the target was spinning itself. And that's all I was allowed to show. But you can see that it is a difficult task to be able to get those two relations together. And then this one is showing the seafloor manipulation through the ROV that was observing the ROV with the arm. So this is two different vehicles with the dynamic positioning, with station keeping. The depth was about, I want to say 7 meters in a surf zone, so that you did have surges coming back and forth, and as you can see the mouse. You know, it's not constantly having to adjust for that. That's all being done by the software itself. And you can also see the arm moving in the sonar. So we found this to be a very successful demonstration along with Seabotix, that we were able to make the vehicle stable even no matter what the arm was doing. And we're poised to go to the next level with Seabotix and the UMV lab. Currently, for manipulator operation, you still do need 2 people, especially since the target is moving. So you want, for those floating ones, that there was really somebody needed to move the ROV, even with the dynamic positioning, and somebody move the arm. But I think we're very close, especially with like the new technology with visual tracking, that we can move to 1. And eventually we would like to make it so that anybody can just walk up and actually perform operations. And these kids were actually flying the ROV. They were able to fly by themselves within like 30 minutes. Future advancements. So other future advancements is also, you may not need, that stable ROV. You may not actually need 4 degrees of freedom on an arm. You could add degrees of freedom to the ROV for control. Right now we're just stabilizing. We're just stabilizing in the pitch and roll. But if you actually command the ROV to do the other degrees of freedom, you may not need as complicated of an arm. You could possibly do everything that the ROV can do itself. Also, visual target tracking. We can do sonar target tracking very well and keep in relation with a hard sonar reflection, but you probably cannot see that too much. But we also have visual tracking capability, and we would like to see that also be used for mine countermeasure and for lots of other things. Oh, that one has sound. So, there's no reason to hear thrusters. So SeeByte is also, we also do the AIV, which is one of the most capable autonomous vehicles in the ocean. It's for oil and gas, for Subsea 7. It's an on-station hovering AUV that goes out, inspects, comes back, all autonomously. It's still very large, so another thing that we could be moving toward is a very small on-station ROV that just goes out and does its job and comes back and it reports what differences it sees if somebody has come up and clamped on something or if there's an object of interest. That's what it goes after. And this is a video of the AIV autonomously docking. This is another view of it just coming in. I'll skip through this. There's another view of the AIV coming in and autonomously docking. So somewhere, I'll quickly go through this. This isn't really an engineering talk, but I do want to say that coupled control is also something for the future. We already have PhDs working on this at Heriot-Watt. We have it working in simulation, haven't tried it on hardware yet, but coupled control is also really the future where not only can you click on a video and the ROV stays at a certain distance from whatever's on the video, but you also click on that video with an object of interest and then the ROV and arm moving together as one entity to do something with that arm. So you could right click and say, grab that. You can right click and say, do this other pre-programmed thing to that. How we do that is we really separate out the force and the position control feedback loops. If anybody's interested, I gave a presentation at Oceans along with a paper, and it's public use, and anybody can take a look at that. But it's very interesting stuff that's coming down the line for that. And that's all I have. But Teledyne Marine. Everywhere you look.